It gives me great pleasure to introduce Kostya Novoselov to you from University of Manchester. I'll tell you a little bit. Kostya has a number of accomplishments to his name, so I won't enumerate them all. I think it will embarrass him. So I'll tell you a little bit about what graphene and his accomplishments and what they mean to me before we get started. Kostya is best known for his work he tells me he doesn't like the word discovery, and I'll tell you why in a minute, but his work to experimentally isolate the material called graphene, and that happened in 2003, 2004, and led to the Nobel Prize in Physics in 2010, which Kostya shared with his colleague Andre Geim, also at the University of Manchester. I've worked in the field of carbon nanomaterials for a little more than 20 years, so I was certainly aware of this work when it happened. It's a fascinating story. So graphene actually was a word that we used all the time to describe carbon materials. So graphene is a single atom thick plane of carbon. And we worked on materials that in some sense were constructed from graphene. Carbon nanotubes, which are cylinders of graphene, fullerenes, which are little spheres of graphene. But graphene was this theoretical construct that wasn't available in the laboratory. And in fact, we understood it. We knew the properties that graphene should have if it were to exist in the laboratory. But it was, many people felt that graphene was an impossibility, that this flat sheet of atom-thick carbon wouldn't exist by itself. It wouldn't be stable. It would roll up, or it would fall apart, or it would be too hard to produce. So it was surprising or shocking even that it was produced, and the work that Kostya will tell you about tonight took everybody by surprise. In fact, it even came from a group of scientists that wasn't really working in carbon. So they were dabbling, right? It's more than that. They did something that really people considered impossible, and they made it easy. So graphene immediately was available to laboratories around the world to study. And that led to the discovery of a number of amazing properties, many of which were not anticipated before the material was available. And nowadays graphene is very exciting. Myself and other researchers here at the Monash University, we have the Monash Centre for Atomically Thin Materials just formed, where we're working on applications of graphene, all sorts of things, membranes for water filtration, biomaterials that can be implanted. So all sorts of things that we never dreamed of before this work that Kostya will tell you about. But it's important, I think, to remember when Kostya tells the story that this was all started with a piece of work that was really curiosity-driven. That's basic science, discovery-driven research, without any idea of exactly where it would go. We didn't think, oh, we're going to do this because we want your mobile phones to be flexible, so you can fold them up and put them in your pocket, or to have a battery that charges faster, or something like that. This work was done really to find out what are the things that are out there that we can make, and what are their properties. And so I think that's maybe that's an important message I hope you think about during the talk. So enough from me. Let me introduce Kostya Novoselov, who will give us a wonderful lecture, I'm sure.
Good evening, everybody. It's a great pleasure to be here, and I would like to thank Michael for this invitation. He invited me to attend a very nice conference which is going on now. also I use this opportunity to give this talk as well. So let me start not with the materials, but just with a story. We just, similar as Michael has told you that he is creating his center of two-dimensional materials. We just finished the construction of the National Graphene Institute in Manchester, so that's how it looks at the moment. That's how it looked 2 years ago when we started the archaeological survey. And what can you dig out in Manchester? Not much. So we had rows of terrace houses from 1790, 1820, but also the remains of a fairly large building over here, which has been identified as an Albert Club house. And the Albert Club house was the club for German expats in Manchester in the beginning of Industrial Revolution. And we probably won't remember much about that, but this gentleman was the member of that club. Now, I'm sure that this face doesn't tell anyone anything in this audience. People in Manchester would recognize the guy, the German guy with a beard, Industrial Revolution. It's Engels. And because his father owned some of the mills in Manchester, and he worked on those mills for some time, also had quite a turbulent life at the same time. And every single building on the University of Manchester campus is supposed to be named after a famous Mancunian. Physics is Schuster building, math is Alan Turing building. So we immediately thought that the National Graphene Institute should be the Engels building. Then we went to our government with this idea. They immediately reacted that we give you money to do research, not to explore your communist past. And so we waited until the last general election. It didn't help. So we still have the building without the name. But similarly, as the Communist Manifesto hasn't been written by one person alone, although it's called Graphene Institute, we're not going to study only graphene in it, and we are going to study all the other two-dimensional crystals, same as Michael just mentioned for his center, and that's the topic of my lecture today. Not only graphene, but all the other materials in the Flatland. And you already probably recognize that I stole the title from this famous book of Edwin Abbott Habit, and same as the book itself, this talk will be of two parts. The first part is this world, the two-dimensional world, and then I will show you how do we transit to the three-dimensional world. So, graphene. Soon after people isolated it, it became a very popular topic for research because of its multiple superiorities. It's of course the thinnest possible material, it's the strongest possible, the most conductive, the most thermally conductive, and so on and so on and so on. The most important property in this list are those 3 points, because we come across new, interesting, fascinating properties every now and then. The most exciting part is that it's extremely simple material. It's only carbon atoms arranged in honeycomb lattice. It's a 1 atom thick fabric. However, although it looks very simple, it's not one of the simple Bravais lattices. You would require 2 atoms to describe this lattice. I colored them red and green. Of course, it's wrong. We all know that carbon atoms are blue, but just to distinguish between the 2 different atoms, and you could see that all the green atoms would have a neighbor from the top, all the reds would have a neighbor from the bottom. And because I need 2 atoms to describe this lattice, when I talk about electrons, I need to think that this electron in the quantum mechanical description, I need to allow to this electron to exist simultaneously on both sides, and if I do it, I would have to create two sub-bands, and then those bands they cross at certain points in the Brillouin zone, and it gives me the very celebrated linear dispersion relation. Now I probably said too many words already. Let me try to explain you what is the significance of this hexagonal symmetry and the significance of this unusual dispersion relation. Well, most of the materials, conductive materials, can be divided into two classes. Those where electrons conduct electricity and those where holes conduct electricity, N-type and P-type, negatively charged quasi-particles and positively charged quasi-particles. Things like gold and copper is electron metal, aluminium is hole metal, and so on. If I want to make an analogy in the real world, it's like a country with single party system, and then people would be electrons or quasi-particles, and then you're fine if you want to move within this country. However, if you make a junction between those two, you connect those two materials or two countries, and then you would immediately create a border control, and you can control the people crossing this border or electrons penetrating through this junction. And that's basically how modern electronics work. You need two materials of two different types, N-type, P-type, electrons conduct electricity, holes conduct electricity, and then you connect them together, create so-called p-n junctions or border control, and then you can control the current flow, and that's basically how your transistors operate. Graphene is very different. You have both electrons and holes at the same time, and they are described by the same wave function. So the analogy of the country would be United States, where you can have the state can be either Republican or democratic, but you still can cross the border between those states without any problem, and that's what happens to the electrons in graphene. They can move through the crystal through any junctions without being scattered, and that's why it conducts electricity so well. You can go even beyond that. You can create more exotic quasi-particles. Say you take two layers of graphene, put them together, you have much more exotic quasi-particles, but I haven't got an example of a country for that one, so I'm not going to talk about bilayer graphene. So as a result of this interesting property, we can use graphene for transistor applications. It's not very good transistor in terms of, well, you cannot really use it for logic application, but some of the parameters are very good. The parameter which tells you how fast your electrons move across the crystal is called mobility. The figure of merit for graphene would be 250,000. At low temperature, it's even higher. If you compare it to silicon transistors, which are in your computers, it's 1,000. The best hemmed devices, which are in your mobile phones, is 50,000. So graphene is already doing much better. And that's all because of its hexagonal symmetry and the very specific electronic band structure. The problem is that the very same electronic band structure doesn't allow those electrons to stop, and for a transistor you need to have both on state when it conducts electricity and the off state when it doesn't conduct electricity. Graphene always conducts electricity, and you can't do anything about this. So it's only certain types of transistors are possible with it, but later on I'll show you how we can overcome this issue. Then optical properties are quite unique with graphene as well. And you can ask, what kind of optical properties can you expect from a fabric which is only one atom thick? I've got millions of atoms between me and you in the air, and I still see you perfectly. Well, graphene, or even though being only one atom thick, apparently you can still see it. It absorbs quite a sizable fraction of light. Here is a device where we have just an aperture and then some of it covered with graphene, 2 layers of graphene. There is nothing here, and you can see a contrast. This contrast is about 2.3%, which is quite a measurable value. The interesting part is that this number, 2.3%, is given only by the combination of the fundamental constants. It is pi times alpha. Alpha is the fine structure constant. Do it at home, 3.14, divide by 137, you get 2.3%. So if you ever forget the most fundamental constant of this universe, the fine structure constant, you take graphene, look through, measure the contrast, divide by pi. That's the most fundamental constant of this universe. It's quite easy to measure. 2.3% for a physicist, it's a huge number, very easy. At the same time, for any device engineer, they would kill to have a material which absorbs only 2.3% and would be as conductive as graphene, because it can form the basis for any transparent conductive coating which you require for LCD displays, touch panels, solar cells, and so on. And here is an example of a liquid crystal device like this, where we replace the traditionally used material, indium tin oxide, with graphene, and it does pinch off the optical transmission completely, so it operates well. And here we benefit not only from the high conductivity, good optical transmission, but also from the fact that it's flexible and it is mechanically strong and it is chemically inert as well. And this tells us that probably applications with graphene should be quite realistic. Now, before going into promises what graphene is going to do for us in the future, let me tell you what graphene has done for us already. Well, it created workplaces. Some of my students opened their own spin-off company, so they're doing okay. It was meant as a joke, but then 2 years ago I received my regular copy of Glamour magazine, and on one of the pages you read 5 jobs our kids will be doing, and then right next to virtual architect, avatar stylist, and active makeup developer there is graphene engineer. And if said by Glamour, then it should be true. Okay. It also provides entertainment. I'm sure that I don't need to introduce this sitcom in this audience. Good. And okay, so in one of the episodes, Sheldon is trying to resolve the issue why electrons in graphene behave as massless quasi-relativistic particles. He struggles for the whole episode long. You all know this already, but he struggles, and the reason why he struggles that those formulas are wrong. It's for bilayer graphene, it's not for monolayer graphene. It also gives shelter. If you bother to live in Tallahassee, Florida, you can live on graphene lane as well. Now, however, and there are quite a few other applications similar or more serious as well. Now, what I like to see is some applications where graphene doesn't simply replace an existing material, but actually creates new applications which were not possible without graphene, where we use all the combinations of those superlatives which I already mentioned to you. And here is one of such applications. So we create adaptive contact lenses, and how you do it, you take a contact lens, basically plastic, PDMS, cover it with graphene, put another one on top and fill the gap with liquid crystal material. And basically, because you can apply voltage here, you switch the refractance index of this liquid crystal, and you can change the optical power, the focal depth of this lens. So you can change it by 0.7 dioptrium, so which is quite a reasonable number. That's what you need for your contact lenses. And because those contact lenses need to be curved and needs to be flexible, the traditionally used transparent conductive coating won't work. It basically cracks and stops conducting. Graphene is very strong. It doesn't crack. It follows the surface. It works really well in this application. Generally, one of the most probably interesting and exciting application is to use graphene as a membrane. Although it's only one atom thick, it's completely impermeable to any atoms. At the same time, we know how to modify it and how to create controllable holes in it, and then we can make it permeable for certain types of atoms or molecules, and then you can use it for various barrier coating or membrane applications. For example, you can grow it on top of copper, and everywhere copper is protected by graphene, it doesn't corrode. Or one of the cheap way how to produce graphene is through graphene oxide. So this material is called graphene oxide paper, and it has this very unique property that it doesn't allow anything through a part of water vapor. So water molecule comes in, opens a pore and passes through, but nothing else can go through. So you can use it for water purification, for example. And generally, this membrane technology, because you can make it compatible with the biological membranes, I think it gives lots of potential applications in healthcare and biomedicine, like artificial organs, tissue modification, drug delivery, sensors, and so on. And quite a lot of work is being done already in this direction. Coming back to transistors, I should say that high-frequency transistors are being developed and work fine. However, if you try to use it for logic application, as I told you before, we face an issue. There are several ways how we can try to overcome this, but later on I'll show you more elegant way how we can produce transistors, good transistors for logic application based on graphene. But generally, high-frequency applications are good, and here is another example of such an application. It's a terahertz laser, so you can use it for telecommunication, and graphene can be used as a plasmonic waveguide, because we can change the parameters of graphene. We can modulate the light which is coming from those lasers. So applications are realistic, however, subject to mass production. I showed you this example of the liquid crystal display, and it was only 1 pixel, 30 microns large. Of course, for your TV, you don't want 30 microns, you want at least 30 inch. How are we doing on the mass production side of graphene? So for some time, it was an issue. It's been resolved some time ago, but before going into different ways of producing graphene, let me put it a little bit into historical perspective and tell you about the mass production of graphite. The reason I like this story is because the first ever graphite mines are very close to Manchester, in a very picturesque place in Borrowdale. In the Peak District, you still can go to those mines, collect some graphite, and graphite was a strategic material because it's been used not only for pencil. Well, pencil was important. The first mention of graphite is 1555. 1565, we already see the first depiction of pencil made from English graphite. At that time, they call it English antimonite. They didn't know that it's carbon, that it's graphite. Published in the book of Konrad Gerstner in Zurich in the year of his death. So the people who owned those mines, they realized the strategic importance of this material early on, and they limited the production of graphite, inflating prices artificially. So at certain moment, a pound of graphite costs a pound sterling, and at the same time, the weekly wages of the workers, of the miners, would be maybe a few shillings. So basically, it created a huge problem with illegal access to the mines and stealing of graphite, because you basically put a rock of graphite into your pocket, and here you are, you've got monthly wages in your pocket immediately. And of course, the owners didn't wanted to do something, and they pushed for a special legislation through the parliament, which and the punishment for illegal access to the mines and stealing of graphite was public whipping and hard labor, I guess, in Australia. And every time a new student appears in our lab, so I remind him or her that this law is still enforced, and if you touch graphene in our lab, you are condemned for 4 years of hard labor as a PhD, and then public whipping at your viva. And even the very title of this slide, the black market, they say it originated from the illegal market of graphite, which existed in 17th, 18th century Britain. Now, these days there is a fairly legal gray market of graphene, and I showed you already some of my students open companies. One of them was Graphene Industries, one of the first companies operated on this market, and they started to sell graphene at some ridiculous price of £1 per square micron. And in the beginning it was okay, so the samples were of the size of a square micron, so they could barely afford postage expenses. However, the process developed, and we were producing better and better graphene. So these days, millimeter-sized crystals, monocrystals are easy, maybe even more, even larger. So if you extrapolate this price, you get to some ridiculous number. I keep telling him that it's not a sustainable business, but apparently he's still doing this. But luckily, these days we can go from flakes, from making those small monocrystals, into mass production of graphene. So generally, in the lab, we would produce graphene by Scotch tape method. Just take graphite basically from the pencil and then exfoliate it with the Scotch tape. But depending on the particular quality and the price which you want to pay, there are many other methods as well, like liquid phase exfoliation, which is suitable for energy applications or composite materials applications, or CVD grows, which gives you monolayers in square meterage, and a few other slightly more exotic ways how to produce graphene. And this brings me to the second part of my talk, where I want to go to the three-dimensional world. So, as I said, we would typically produce, in my lab, we would typically produce graphene from graphite, which you can find in your pencils. And my students, they're all very active, bright eyes, bushy tails, keep asking me, Kostya, you just build this new building, put all the equipment there. Can we finally afford to buy not only the lead pencil, but also some other pencils as well? Yes, we can. And the trick is, if you exfoliate other pencils, you can create other materials which are only 1 atom thick. And if you do that, you basically create a new class of materials, which we call two-dimensional crystals. Many of them are stable. Those which are not stable, we do understand how to operate them still. And what is interesting, that the properties of those two-dimensional crystals are very often different, or very different from the properties of the three-dimensional counterparts. And this gives us quite a unique opportunity, which I just want to summarize in a couple of slides. If you think about it, there are only a few materials which determine our world. Like electronics, it's all silicon. construction engineering, basically steel, aerospace engineering is aluminum, titanium, and we don't notice this anymore. We simply learned how to cope with those few materials, and few materials means few opportunities. If you're an electronic engineer and you want to design a new device, what you do, you check what silicon can do for you, the band gap, and then you create, or mobility, or whatever else, and then you create your new device in accordance to those parameters. Now, ideally, of course, you don't want to be bounded by those parameters. What you want, you want to combine different crystals and different properties in one device. In principle, this concept is known as composite materials or heterostructures, where you combine the best of different materials. And it does exist, it's being used in engineering, but those examples are still few and far between. Ideally, what you want is to be able to create a completely new material from scratch on atom by atom, or at least layer by layer basis, and then you would be able to, say, encode certain parameters into those materials and into this heterostructure. And for example, my top layer of atoms would be a sensor. The next few layers would be solar cell to empower this. The next one would be some logic, interconnects, reinforcement, and so on. And because we now have this family of two-dimensional crystals available to us, we basically got a library of those materials. What we can do, we can start getting those one atom thick crystals and start putting them together into a heterostructure, something like this, but in a way Mother Nature ever intended it to be. So I can mix many different crystals all together, and each one of them would give me certain functionality, and then combinations of them would give me some new functionalities. For example, those top 6 layers would give me a transistor, and it's really good transistor. Then those few would give me solar cell and so on. And because I've got quite a large range of those crystals available to us, we can create transistors and electronic devices with very different characteristics. Just to give you one example of how widely spread and those layered crystals and what we can do with it, here is an example of slightly unconventional transistor where we use very special material as a tunneling barrier. So we use vermiculite, which is basically clay, as a tunneling barrier. And the reason why we did it, because it's widely available. It's widely available in any convenience shop because it's the basic element of the catalytic boxes field. So what you do, you go to this convenience shop, you buy this catalytic boxes filler, and you can create your transistor out of it. And so it is in the off state if you apply negative gate voltage. It's in the on state if you apply positive gate voltage, and also because those clays are sometimes piezoelectric, so you can use it as a memory device as well. And the only trick you need to remember is that you need to use it before it went into the catalytic boxes, or not after. So the technology is a little bit tedious at the moment, but we're working on this. But basically, our students do exactly what I said: take one atom thick fabric, put it on top of another, take another one, put it on top of another, and just do it many layers. But because we can control it very well, I can show you the quality of the resulting heterostructure can be extremely high. So we can take this heterostructure, cut it away, pull it out, and look at it in the TM, and you could see all the individual layers, so those lines are individual layers, and you can see, so here is boron nitride and graphene layers together, and you can see all the sequence without much contamination. Here is another example like this. It's also boron nitride together with bilayer graphene, and then there are several alternating layers of boron nitride and graphene on top of each other. And if I show you this dark field transmission electron microscopy image, then you probably won't be able to say where the boron nitride, the bulk boron nitride stops and where graphene starts. So the quality of those heterostructures can be extremely good, and also electronic quality can be very good as well. Now, what I thought I would do, I will give you two examples of what we can do with those heterostructures. One is more about physics, science, and one is more about applications. So in terms of the science, I chose a very simple structure, just simply graphene on top of boron nitride. Boron nitride is very similar to graphene. It's also hexagonal, has a hexagonal structure, but unlike graphene, it's a very good insulator. But because the atoms of boron and nitrogen still interact with carbon, what I get at the end is a periodic potential for electrons in graphene. It's like you take two crystals, any periodic patterns, you put one on top of each other, and if you rotate them slightly, what you see is the so-called mirror pattern, and that's exactly what happens for our graphene on boron nitride, and that's what you see in those STM images. So this pattern are not atoms, is the same mirror pattern which I show you here, and this gives me a very specific property of the electronic structure. Basically, a part of this cone which I always had, I get some smaller cones a little bit outside at different energies, which gives me, which is quite an interesting object by itself. So I will get new type of quasi-particles. But what is interesting that if I apply magnetic fields, I get yet even more interesting particles, which consist of electrons scattering in this potential, but also they acquire one flux quanta of magnetic field. So it's quite a complex quasi-particles, but their properties are extremely exciting, and it's a good fun to study those. And it's simply because we can interact two layered materials, graphene and boron nitride. Very simple structure. Another example is way more complex, so it would take my student maybe to a whole week to create a structure like this. So it's quite a few layers to put one on top of each other, and a part of graphene, boron nitride, also use some other semiconducting materials as well here. But at the end, if I make it, it will turn into LED, into light emitting diode. So if you apply voltage, you get light out of the structure. So it's quite exciting, because you basically started with monolayer of different crystals, and you put 10, 20 of those layers together, and at the end you get something which emits light, and we can control the wavelengths of this light emission, or and the quality, or you can mix different valences as well. Now, because it's still, even though it looks quite a large structure, it's still 10, 20 atomic layers, and because of that, it can be transparent and it can be flexible as well. So it still can form the basis for flexible and transparent electronics of the future. Now, this is of course all very much into the future electronics, and it might take another 5, 10, 15 years before we know how to grow it in large areas, although we had the same feeling for graphene 10 years ago, and the progress of mass production was really enormous. But it's science, and we cannot really predict how it's going to develop. But already now we have a cheaper way how to produce those heterostructures, because one of the way how to produce graphene is through chemical exfoliation, and basically what you get is a suspension of graphene. We call it graphene ink. And you can make inks of many other materials as well. And now what you do, you basically start, you put those inks into your inkjet printer, and you start printing those heterostructures literally in the inkjet printer. So you just print one layer first, then another one. You can put contacts on the way, and so on. And basically, at the end, you can get either a transistor, or you can get a solar cell as well. So if you shine light, you can get some photocurrent out of it. It doesn't work very well, but at the same time, it's extremely cheap. And imagine you simply have got 3 paints. You paint on any wall 3 layers, and your wall turns into a solar cell. So it's that simple. And of course, because it's still a few layers of atoms, those structures are still very flexible and very transparent as well. So this basically takes me to the end of my talk, and let me say that there are, surprisingly, after 10 years of extensive research on graphene, we still find lots of exciting physics in this material, but even more, we see much more of this excitement in other two-dimensional crystals. And we also see lots of possible applications, and what is encouraging is that we see other materials as well gaining interest from our industrial partners, and in some areas we see that other materials are actually overtaking graphene because they've got some special properties. And of course, the most exciting part is that we would really like to see some applications which we couldn't possibly predict, which were not possible without graphene. So those are the most exciting applications. And I would like to thank all my collaborators as well, and in Manchester and in some other universities across the world. Thank you so much.
What happens around the edges of the graphene? The carbon atoms are not fully bonded.
Right. So it's a very good question, and what happens is whatever you want. So the easiest way to answer would be, if I would be a theoretician, I would say that I can bond whatever I want. So those edges, typically hydrogen, I can bond oxygen as well. The properties of the edges might be quite exciting, because you can get magnetism out of those edges. You can get one-dimensional channels. In reality, of course, because of lots of disorder at the edges, the properties are very hard to study. But at the same time, depending on the particular experiment and on the particular application, people do certain tricks how to control it. In transport experiments, like it's less control available, although there are some reports on the magnetism which arises from the edges, which would be quite exciting to have magnetic carbon. That's something on the agenda for many scientists. But people who work with suspensions of graphene, and those are people who would like to use it for energy applications like supercapacitors or batteries for composite materials, biology quite a lot. They like to functionalize those edges with particular species, chemical species, and they would gain certain extra functionality, which allows you to penetrate through biological membranes or instead bond certain chemicals like for drug delivery. So so that area is quite active, and people know how to modify those edges.
In air, would you expect oxygen to attach?
Well, it depends. Oxygen or hydrogen, depending how you create. There are interesting reports. If you have two layers of graphene together, they can actually close to itself and form half of the carbon nanotube. So there are experimental evidences for such behavior. So we can control it.
Graphene is always presented as a perfect, ideal structure. So I'm just wondering, when you make it experimentally, to what degree is it ideal? To what degree does it have defects and imperfections?
Right.
And whether these, if there are defects and imperfections, whether these may be important in some applications.
Right. Well, again, it depends who makes those samples. The reason why in my lab we stick mainly with this Scotch tape method, because we actually make perfect graphene. It's hard to believe, but you will spend weeks trying to find a single defect, a part of the edges. So it's that perfect. And then if you want to study defects, you would typically create them artificially. So it can be extremely clean. So because carbon-carbon bonds are extremely strong bonds, it's very hard to create defects. So it is possible to make it perfect. When you grow it by other methods, it's not as perfect. But then at the same time, the growing techniques improve all the time, and these days you can get very good quality. In terms of defects, yes, there are. You can make some interesting physics on defects. For example, grain boundaries can give you specific scattering, and you can get 1D channels on the grain boundaries, and those experiments are performed. It's just how to obtain in a repeatable manner those defects. It's easy to create one defect in the lab if you want to use it for certain applications and you want to create millions of them and in a controllable way. Well, it might take some time.
I'm a student from the Department of Chemical Engineering. My question is not related to the specific scientific things. My question is, did you encounter some difficulties during your research career, and what is the most difficult period during your research period, and how did you overcome these difficulties?
Okay.
Thank you.
I think, well, actually, no. I know how to answer this question, and to be honest, the current paper is always the most difficult, because you always see, okay, those which I published a year ago, wow, those were easy, but the current referee is really giving me a hard time. So believe me, and I'm not joking. So I'm talking to you and I'm thinking, how the hell I'm going to answer that particular nasty referee which just sent me those referee reports. So you experience difficulty all the time. It's impossible if you chose a career in science, be prepared. It's a miserable job. So you're fighting referees. I was fighting them when I was a PhD student, a master student, PhD student, postdoc. lecturer, professor, and I'm still fighting them with the same passion. So it doesn't change. It's not going to get better. Sorry.
I was really inspired by your starting 2D materials like graphene and other kind of 2D materials to 3D to achieve really wonderful properties. The question I have is, just like the graphene is very different from the graphite, which is a three-dimensional type version of graphene. We might also expect that during the process of starting 2D materials to 3D, the property that you expect or anticipate it to be might change during the starting process. So, and it's really related to the bonding between two layers, the orientation you have talked about that can create the Maury fringes, and also many other relationship between those materials. So I was thinking that like during the starting, the number that we are starting at, the number of layers, and the orientation and the type of layers that we are starting, is that currently just like testing, like try and error, or is currently a more systematic way to make those progress?
Well, it's a good question, and of course you would hope that it could be more systematic, and I'm trying to be friendly to many of my colleagues who do theory and DFT calculations. The problem is that very often those calculations are extremely challenging, and the interactions which we are talking about here are mainly on van der Waals level, so which are very hard to predict and to calculate. So the best way how we are doing this is to use your scientific intuition, what might happen in those structures, create those structures, see the property, and then give certain direction to your colleagues who do theory, and then just together try to resolve what is going on. So it's a continuous interaction, and you can't rely only on theory, and experiments do need theory support at the same time.
Any other questions?
Just going to ask you, how strongly do the multi-layered structures stick together? What sort of bonding occurs between the layers, and will those weaken over time so the layers will slide away, and or are they very strongly bonded together when you stick them together like that?
All right. Okay. So the bonding is mainly the type of bonding which we mainly use is van der Waals bonding. Well, it's quite strong. If you those layers once you stick them together, it will stay. However, certain orientations of this van der Waals bonding are more preferable. So sometimes we see those crystals even rotating macroscopically simply by themselves without any input from us. So it's an interesting system, and I mean, having something rotating mechanically on micron scale, it's quite exciting to see, and then you would know that it's all because of the crystallographic alignment of the crystals. So it's quite a strong quite strong bonding, and those structures are usually extremely stable.
There's one question about the transistor performance. You mentioned that the standard on and off ratio should be above 100 or something.
Right.
And the performance with your two-dimensional materials fine? Or?
Okay, so the transistor performance in terms of on-off ratio depends on the particular application. For high frequency transistor, you basically use it as a voltage to current converter, and then on-off ratio of 10 or 100 can be enough for that. For logic applications, like in the processor of your computer, you need usually 10 to 6 or at least 10 to 5 on-off ratio. Otherwise, it would overheat all the time. So graphene, if you try to use simple field effect transistor, it can give you 100 on-off ratio, maybe a bit less. But
can you actually control that ratio with the material?
Well, you can. It's given by the mobility of your transistor.
But the mobility may depend on the geometry.
Mobility mainly depends on the quality. So let's say graphene operates reasonably well, or actually quite good, for high frequency applications. Now, if you want to use it for logic applications, you have to play tricks. So single electron transistor is one possible trick. Tunneling transistor is another possible trick. And then, so there are transistors which are based on graphene, which can be used for modern technology. The problem is that they are either hard to make, like single electron transistor. It requires really control on the nanometer scale, much beyond the modern 6 or 7 nanometer technology, or they require completely different architecture, like 3-dimensional stacking, as I showed you, which is not what modern silicon technology is using. The silicon technology is planar technology. So there are solutions, but how technological are those solutions? It's a good question. So what you have here are two people who've been working with graphene for longer than anyone else. So touch wood, we're still fine, right? So
the question, maybe I'll repeat it, is what happens when graphene is introduced into the body versus the body?
And of course, school kids been chewing graphite pencils for ages now. Now, seriously, of course, any new material needs to be studied, and for toxicological aspects in particular. Currently, what we know is we haven't found big toxicological problems, although graphene does interact with certain types of cells, so we still need to look for it. It hasn't been found any carcinogenic effect, although it can penetrate through certain membranes. But it really depends a lot on the type of graphene, because there are different types of graphene. It can be thick, thinner, small. Some you can make it hydrophilic, you can make it hydrophobic, and the reaction really varies. For example, my colleagues try to use graphene for medical imaging, and they use the fact that if they introduce graphene into the blood system, it would stay in the body for quite a long period of time, but then after 24 hours, most of it would be excreted. Another example is there are lots of reports of graphene oxide. It's the oxidated graphene having antibacterial properties. I was trying to use it for certain applications, so I thought it's really fantastic. If you can spray it on a wound, it only allows water through. The wound would dry by itself, but then it won't. It would kill all the bacteria. I've been doing it for more than a year now, and I failed to kill a single bacteria so far. So it's a big area of research, and there are lots of parameters. There are some good results, some bad results as well. But let's say so far it hasn't it hasn't been found that it's cancerogenic. It's probably not. And for the rest, it really depends on particular parameters. Thank you.